we're here. So pre-stressing of a structure, that just means applying a load to a structure to counteract a load that's going to occur during its design life. So there's lots of other definitions if you go Googling on the internet. Typically when we think of pre-stressed, we think of concrete, though it's not limited solely to concrete. A simple example of pre-stressing is picking up a row of books. As illustrated at the bottom of the screen there, if you have a stack of books, put some force on to confine them and push them together, the frictional interface between each of the books generated by the axial load that you're applying allows you to pick those books up nice and easy. That is effectively a pre-stressed operation, very similar to that used when you're doing precast segmental bridges. So it's a very similar idea. You might not think of these items as pre-stressed, but all of the ones on this screen here are pre-stressed. Some you'll be more familiar with than others. So an umbrella has tension skin, which is what keeps the water off you, acting in conjunction with the spines or the metal bars that support that structure. That's a form of pre-stressing. The saw in the center there, I'm just going to get a pen here. So that's your saw blade just there, and the action of, and it's pinned there and there, and the action of twisting this leather or rope at the top here causes this to, there's a pin there and there, and as that gets smaller, as it's tightened up, it pulls these in and these in, which puts the saw into tension. That is a form of pre-stressing. A bicycle wheel, you've got a hoop made of aluminium, steel, whatever it may be, and then all of these rods, the tie rods here, every one of those is under tension, and that's what holds the bicycle wheel in shape. Similar idea with a timber cart tire, where you have your timber spokes and your timber wheel, and around that you heat, that's typically a steel tire, which is heated and then dropped over the timber tire. As the steel cools, it contracts or shrinks, and that puts everything into a stress that locks the cart wheels together. So a very, very early form of pre-stressing there. An even earlier example of pre-stressing here would be this boat I found on the internet. A similar idea where you've got the hull of the boat, and then they've used this stressing system over the top here to put it into tension, a bit like the saw above, the saw that you can see here. I'm going to clear those drawings off the screen. So these are all things you've seen that you might not have associated necessarily with pre-stressing previously. Many different structures or forms of structure can be pre-stressed: steel, cast iron, concrete, masonry, anything you can think of. But typically when we think pre-stressed, then we think concrete. So masonry is fairly popular to be pre-stressed. Things like pressure vessels and reactor vessels for nuclear sites, you've got a cast iron, or it might even be steel, probably a steel pressure vessel of some sort, and around the outside of it you've got high tensile steel bands that have been tensioned up, and that's just compressing the pressure vessel itself, a form of pre-stressing. Concrete, which we're going to go into more detail. Masonry, where you've got your footing and you have a anchorage bar coming up through that you can tension up, and that puts the masonry under a preload, which increases its bending capacity significantly. You can pre-stress steel beams, though it's not very typically done. There are times you can use steel in conjunction with stone. That's an option that's becoming, I've seen quite a few bits and pieces on articles on that recently, where people look to try and use stone as opposed to concrete because of the embodied carbon. And again, if you've got stone, which is generally good in compression, well, it's good in compression, but not quite as good in tension, or you want to use blocks of stone, if you use the stone in conjunction with pre-stressing through steel tendons, you can produce a useful structure out of it. So these are all things we can do. I don't have a great deal of faith in the detailing of this steel pre-tensioning here, in case you're thinking it's a good idea. The angle looks far too weak to be able to put any significant pre-stress into that beam, but the principle is what we're showing there. So why do we pre-stress structures to start with? The key reason being you can produce a more economical design, particularly when you're looking at concrete structures. What you end up can often be lighter than if you've done it out of traditional reinforced concrete. It will be lighter, it should be lighter. You can produce crackless structures. So what I mean by that is if you look at a normal RC beam or wall or whatever you want to look at, there will be micro cracks when that structure or when that part of the structure goes into bending. You can't avoid it. It's inherently part of the system. The tension phase, i.e. where the steel reinforcement bar is, will crack, as you can see at the bottom of the screen. They might be very small cracks, but these cracks are the driving reason why you get corrosion, particularly if you're looking at a water-retaining structure or other aggressive environments. Whereas if you pre-stress a structure, you can put enough compression into the concrete that micro cracking doesn't occur or is much reduced. You can get a longer span out of a post-tension structure, generally deflect less, the fatigue resistance is increased, it allows you to do segmental construction. So these big long span cable stayed or suspension bridges where they have concrete decks, they're often made up with these precast segmental beams. It also allows precast segmental beams for fairly meaty spans as well. The action of pre-stressing also increases significantly shear capacity of the concrete. If you can picture the shear failure that you get with concrete, if you've got a large compressive force acting on the concrete, you've also got to overcome that before you start failing the concrete in shear. So when we talk about pre-stress, which is what I've talked about so far, I mean pre-stress in general, the action of applying force to an object to increase its capacity in some way. Within concrete, there's two different ways of doing this, broadly speaking. There's pre-tensioning and there's post-tensioning. Pre-tensioning being where you stress the steel, then cast the concrete around it. Post-tensioning being where you form the concrete and then you apply the compressive force to it. So that's the two differences we're talking about, pre and post-stressed. On the left there is a good example of pre-stress, so you can see the tendons here. Let's just get the pen in. So that's each of these here is the, that's the wrong button there. So each of those there are the pre-stressed tendons. So those are precast beams, and if you can picture it, you've got your formwork set out in the factory, the tendons are placed in and they're put under tension, and then you pour the concrete around it. And then once the concrete's cured sufficiently, you can release the tension, which is locked in, so then gets locked into the beams themselves. With post-tension structures, you've got your ducts here, get this right in a minute, the ducts here, and then the tendons are here, and this is the other end. So there's clearly ducts and tendons there where the concrete's poured and then those tendons are stretched to apply the force to the concrete structure. Exactly as I've explained here. So your form is filled with concrete, it's released here, and what you get is this, it's called the Hoyer effect, but as the steel section is cut through here, it will shorten, because any steel or any object that's stretched, not any object, but most objects once stretched, will reduce in cross-sectional area. So as you cut through the tendon and it releases that tension, the steel will swell back up, and that's what locks it into the concrete. It's called the Hoyer effect, if you want to read more about it. Typically speaking, that occurs over 40 to 60 diameters of the strand before you get your full anchorage effectively, and then the full stress in the tendons from then on afterwards. And there's some further examples. Hollow core slabs, big U-beams, T-beams, T-wire beams, all of those typically pre-stress. You can see here a lot more tendons at the bottom to counteract the bending stresses, and then you've also got tendons up here just to try and keep the whole cross-section under fairly uniform compression. Post tensioned, you cast your concrete with a duct in place. Once the concrete's reached sufficient strength, you tension up the tendons, and that puts the compressive stress into the concrete. You then, ideally, that will then be filled with grout, and that locks the stresses into the concrete. So key giveaways with post tension is you'll see the anchorages at either end, or dead end anchorages. You'll have vent pipes and you'll have grout tubes that were used to fill it up. There's a little video here just to run through. It's not in English, but your formwork goes in, place your rebar cage, and there you can see the tendons. Also, there you can see the ducts with the tendons projecting out either end. Concrete is being cast and cured sufficiently, and then you jack and extend the tendons, which is what puts the tensile force and therefore the compression into the concrete. And then the all-important grouting up the ducts when you're finished. We'll come on to why that's really important afterwards. So if you're coming up, or you're involved in demolition or even temporary works, you want to have an idea of where you can find pre and post tension concrete. It's important you understand the difference between the two, and then how to deal with it once you have found it. So pre-tensioned items are normally things that were made off-site and then delivered to the site and then installed. So it's normally not going to be huge items. As craneage becomes more and more common on sites, the items that will have got bigger, and you can get some very, very large precast beams. But typically, going back through when it all started, cranes were smaller, therefore the items that were pre-stressed were smaller. But you can find them bridge beams, you can find slabs, beams, lintels, very, very common, balconies, driven piles, fairly common for concrete driven piles to be pre-stressed because, again, they're made off-site. Water tanks, often pre-stressed to limit the potential for cracking and therefore moisture ingress and rusting. Concrete pipes, very often pre-stressed as well. Post-tension is generally things that were cast in situ. It's because of the very nature of it, it's something that you need to make, such as a long span bridge or similar, or in situ slabs, where it lends itself to being done in situ and then tensioned in place. Normally, you have to have some sort of access to where the tendons are. It might be that has then disappeared as the construction phase carried on, but quite often you'll see signs of where there's access to have got to tension the tendons originally. So it's just a case of having your wits about really on site, because it's not always obvious what's post-tension, what's pre-tension, and what's normally reinforced. It's not an exact science. You can't just walk up to any structure and know straight away. There are clues, which we're going to go through, but there's no definitive answers. There's bridges that we've looked at where we thought that's probably post-tension and they turn out not to be. But it just takes some investigation to make sure you understand what it is you're dealing with. Key giveaways, segmental construction. So you can see in the bottom right here, they've clearly been precast off-site, and then they're lifted into place and they're tensioned onto the adjacent bridge section, and they just keep working your way out. Fairly easy to establish if that's the form of construction. Similarly, if the tendons are external, as they are here in the top right picture, it's fairly easy to establish the post-tensioning there. Similarly, if you go inside the structure and you can see the tendons, it's fairly obvious. Record drawings are the best source of information. They might not tell you everything about the post-tensioning system, but there are giveaways on drawings as to what you're looking for, and showing you that post-tension is the likely mechanism for the structure. Anchorage points visible, mortar infill and grout tubes, they're often signs that there was some sort of tensioning. The age of the structure helps. Really, we're talking late 50s in the UK, though supposedly there's examples back to the 30s. Not that I've ever seen one, but they do exist apparently. If you are lucky, there is a plaque on the structure that identifies it as being post-tensioned. This was a scheme put in place, I think, by the Institute of Demolition Engineers. They put in a scheme to encourage building owners to put plaques on the building identifying if the structure contained post-tensioning. Obviously, the idea being to make life easier for the demolition contractor in 50, 60, 70 years' time when the bridge or the structure was being demolished, you would know that there was post-tensioning in place. If you get the drawings, you can see here clear indication of tendons and post-tensioning on this side and pre-stressing on this side. Fairly obvious from the arrangement of the bars that is a pre, and the shape of the beam, it's a pre-stressed beam, and the fact it says showing pre-stressing strands helps quite a lot. I talked on the previous screen about finding mortar infills. So this was a job, I think it's in Ilford, long span beams, and during the site investigation or walk over the site, it was obvious that there was a mortar infill on the ends of the beams, and we broke some out, and lo and behold, you can see the anchorage for that beam. And it's just knowing what to look for and where to look for it, and then finding easy access to it on the site without having to break out slabs, etc. But yeah, they were big spans, so we were expecting them to be something other than normally reinforced in any case, and this just finished the answer off for us nicely. So when we're demolishing structures that are pre-stressed, which is after all why we're interested in it, they pose some hazards that are unusual. So in the investigation phase of the works, if you don't know it's post-tensioned or pre-stressed, then you can end up damaging the structure without realizing it. If you put a core in the wrong place, you can cause release of the tendons, worst case, or damage locally to tendons. You could accidentally release anchorages if you didn't realize where they were or what they were doing. If the structure's not grouted or the tendons aren't grouted, you can get release of the tendons, which may or may not be a problem depending on the detail in the structure. Stress reversal. So there's two things to that. First one being, if you want to lift down a beam that's pre-stressed and you want to change the support positions, you could potentially reverse the stresses, which could lead to failure. It needs to be properly checked by an engineer. There's a few case studies coming up where we've done just that. The best bet is to try and maintain the support position as best you can, though it's not always practical to do that. The other key issue you have in stress reversal is certainly some large buildings in London, they have like a podium level that has been post-tensioned. But not only is it post-tensioned, but it was post-tensioned in stages as the building got higher. So if you start doing a top-down demolition on the structure, as you take the weight off it, you need to be releasing the tendons that were installed in phase with the construction, or you need to be analysing it to prove it's not going to be a problem. So it's quite an in-depth analysis to sort things like that. Non-grouted tendons, as we've said there, they can release and they can fly. Normally, there'll be something on either end of a beam to stop things flying off. But for instance, this case here, there was nothing protecting the end of that beam. So if you release the anchor, release the tendons, and they weren't grouted, then they could fly off the end of the beam. That is the key hazard with post-tension structures. The condition of the structure, often these post-tensioned buildings are coming down for a reason, particularly if the tendons weren't grouted. The tendons can be in very, very poor condition. There's quite a few highways assets across the UK, or there's less now because a lot of them are demolished, where there's actually acoustic monitoring going on just to listen to these tendons and identify how many are snapped, how often they're snapping, all of these things which are important. But if you're demolishing a structure that's already lost 20% of its tendons, you've got to think about how you go about doing that. And loss of shear capacity. So if you cut the tendon and it releases, that can change the shear capacity near the support. which in turn can cause big problems. That was an issue we faced at Churchill Way, which we'll cover shortly. An example of a concrete bridge that was lifted out and dealt with. So this was a post-tension structure, lifted out in one piece, maintaining the support conditions as near as we could to the original support points, and then processing it with a pulverizer. So you can see here the ducts that the tendons were in. You can see the actual tendons themselves. These ones were grouted. So as you crushed locally, the stress was dissipated in the area you crushed. And as you work your way back along the structure, you can release that tension in a controlled manner. Now, if they're ungrouted as they are here, if you can imagine a beam like this, the top one being a tendon with no grout around it, and the one below being a tendon with grout, if you just cut through this tendon, the tension is going to release and the tendon's going to fly out this way and fly out this way. If it's grouted when you cut through it, then it will re-anchor, or will hopefully re-anchor within the grout locally, so it doesn't fly off. So that's why it's important to understand whether it's grouted or non-grouted. I think clients get sick of me asking for post-tension special investigations to confirm whether these tendons are grouted or not. But the reason we need to know is because it makes a big difference to the demolition methodology. A beam that's fully grouted, you can pretty much work back as a normal RC beam. Whereas one that isn't grouted, as soon as you cut through that tendon, you've lost a huge amount of capacity within that beam. So it's a massive difference in how it has to be treated and how the demolition will progress. And it's important that SI is undertaken to confirm that. So what do we need to know as engineers when working out how to demolish a pre-stress structure? Ideally, we want the drawings. And if it's got details of the tendons, the stressing sequence, the construction sequence of the building, that's brilliant. And it makes life a lot easier. If it's a highways asset, or sometimes rail assets, they do post-tension special investigations, which I think are on a rolling, or supposed to be on a rolling 10-year period, where somebody goes in and does a full investigation on the structure to confirm that the post-tensioning is working as envisaged. As I said, it's vitally important to how a structure behaves. So the highways and the rail authorities know this, and they know the importance of checking their structures to make sure that they're still functioning as envisaged. And if they're not, putting things in place. So there were large programs back in, I think, the 90s, 2000s to go and grout a series of bridges around the country where when they'd done the post-tension special investigation, they found that the tendons were not grouted, which affects the longevity and the behaviour of the structure. So they went in and they grouted them all up to ensure that they would last longer. Any other previous inspections and assessments are very useful, and of course any constraints on how we are allowed to approach the demolition works, which is typical to any demolition. We need to know the constraints before we can plan properly. Excuse me. So there's a couple of examples I've gone through before that I'm going to go through quite quickly, and then I think there's 3 new examples in here of how we've dealt with pre-stress structure. So Regent Street had post-tensioned and pre-tensioned beams. The beams in pink on the left and the right of the central span were pre-tensioned, so that means they were built off-site, or they were cast off-site, and they were brought to site and put into position, and the deck was done in situ on top. The blue ones in the central span were post-tension, so they were cast in situ, and then the post-tensioning system was installed and tensioned up as required. So because of a series of constraints, which you can see by looking at the case study we've done on Regent Street and a webinar we've done previously, we had to take out the central span with SPMTs. You can see straight away that that leads to a stress reversal on those central beams. So looking at the analysis, the original moment was here in red, and then it's the moment when we were picking it up. with supports 18 meters apart was something like this. So we had to analyze the structure and justify that it wasn't going to fail when it was picked up. The way we did that was by looking at the steel in the deck and in the tops of the beams to counteract the hogging moment effectively generated by the cantilever. Sorry, hogging moment generated by the cantilever, which we did. It was all approved, and away we went. And there you go. You can see it in practice there. Another one of it up on top of the SPMT, rolling down the streets of Leeds. The pre-stressed beams were a lot easier to deal with because we could lift them out. They were light enough that we could lift out in the timescales available. We pretty much maintained the support condition, so we were about 2.5, or maximum of 2.5 meters in from the original support points, which meant that we could pick those up, and there wasn't really any analysis required to justify that operation. Whereas if you'd been trying to pick it up a lot further in, you'd have the same problem as we do with these beams here, that they go into hogging, and I've got a stress reversal going on. You can see it being lifted out. Churchill Way, pair of 230 meter long structures, in situ deck looks something like that. The walkways underneath were only in some areas, and they were demolished fairly early doors. But the main problem was demolishing the decks themselves, right through the centre of Liverpool. Quite significant height in some areas and limited road closures, all sorts of things. Again, I've done this to death in terms of case studies. If you want to go and watch them on a webinar, if you want to watch it, it's all there on YouTube. The important point to take from this case study is, firstly, due to client side concerns with the grouting on the structure, we were basically forced to design a backup propping system should we lose the post-tensioning effect along the length of the structure, which would pick up and support the structure if we lost all of the post-tensioning effect through these tendons, which is what you can see in the background there. You can also see the Hoyer effect in action here. So this here is a duct. You can see the outer circle is a duct, and these are the tendons internally here. And around it, you can see the grout matrix. And you can see that once this has been wire cut through here, the tendons have retracted maybe a couple of millimeters. And that is exactly what the Hoyer effect would predict, that it will re-anchor over that length, or over a length, which was, I predict, I think it's 2 or 3 meters or so. And you can see it's re-anchored, locked itself back into the grout matrix, which means the post-tensioning is still working. Okay, you might have lost a little bit of pre-stress, but not enough to be worried about. Each of those spans, roughly speaking, the typical span, I think there was 300 millimeters of extension required on the tendons to put the full design tension into them originally. So losing a couple of millimeters isn't going to be a big problem when it's all it's supporting is its own self-weight. See more pictures there, and you can see there that one where it hasn't even retracted, maybe half a millimeter, it's retracted there. I think the worst ones we saw moved 10 millimeters, something like that. The absolute worst retraction we saw. Excuse me. And then, I say, you can look at the full webinar to see it, but these sections were moved out in SPMTs, unloaded, and then they were cut into pieces and shipped off site. And you can see even when they're cut into pieces, the tendons weren't just falling apart and releasing. You can see them there and there, that they were locking together even on those short sections. Excuse me. Old Slade Lane was quite an interesting structure, well, a very interesting structure actually. Not only were the main beams post-tensioned, but this beam here underneath the carriageway was post-tensioned as well. So it was a very interesting structure to demolish and come up with a safe means of demolishing it. So what we did to start is we took off the wings, or the walkways effectively here, and then we broke out the slab units, so these units here. So you're effectively left with this beam here and this beam here, spanning across. We left a couple of panels in just to stop the potential for buckling, failure of those long span concrete beams. You imagine you've got a very long, slender concrete beam, and you've got all the tension from the tendons in it. Doesn't feel like it would take much to cause them to buckle. I know buckling failure is not typical in concrete, but you can get it with long spans and high axial loads, which is what you've effectively got here. Then we took off the back spans, which left us with this section here to demolish. And that was all then broken out. It did sit down onto the containers and they did their job. But this was the safest way we would come up with to deal with this structure. Quite a challenging one to demolish, and I don't think it was particularly easy for the guys on site either to actually deal with. Just memories of a tricky job, that one. Teapot Lane, that only really had a pre-stressed drop span in the centre. And again, maintaining the current support conditions as closely as we could, and lifting it out in one piece. And the important bit again is how we dealt with it on the ground. So didn't know if it was grouted or not. So steel plate up either end, and then a pile of rubble on top, and then you could just break it out. And even if the tendons do release when they're cut through, it's going to hit the steel plate and the rubble, and that's going to stop any sort of potential injuries. Coupled with a good exclusion zone as well, just to make sure that nobody's in the potential line of fire if something does go wrong. So all things that can be controlled as long as you know and you plan for it. Hunter's Combe was another big post-tensioned structure. It was broken up in situ. And again, we had good record drawings on this one. Plenty of detail as to what it was and how it was post-tensioned, how it worked as a structure. All details on the anchorages. And I believe this one was fully grouted from memory. I think there might be one of them that wasn't, one duct wasn't, but I don't know, but they all blend into one. But fairly simple to deal with, just hit it with as many machines as you could, really. Not a great deal of technical skill required on that one. It's basically understanding the structure and then letting the site team go. It did also have transverse post tensioning. I think that was more of a concern on that one, actually, because so you've got the longitudinal tensioning here down the bridge beams themselves, and then you also had transverse post tensioning coming through and holding all the bridge beams together, and they were more of a concern with releasing than the longitudinal post tensioning. This is quite a recent one. This was done this year. Glenfinesse footbridge. So this is masonry arch. And next to it there is the old footbridge, which was a post-tensioned concrete deck. Quite a constrained site in terms of access. Houses around you, lots of trees around you. You can see in the pictures there. And we needed a fairly chunky crane to lift it out. The only real giveaway that was post-tensioning was these ducts, or looked like ducts on the drawings. Didn't have much in the way of drawings. And then the client managed to track down the post-tensioning special investigation report, which is kind of the holy grail when you are looking at structures like this. That will tell you an awful lot about how the structure works, how the tendons behave, or how the condition of the tendons, the condition of the grout. The key thing you're looking for is ducts, tendons, grout, and reinforcement were found to be in good condition. That's great. And the ducts were fully grouted. Obviously, you've got to read the full report, but they're the headline bits that you're looking for and hoping for if you're demolishing one of these. So structure itself was broadly T-shaped, and it was to be lifted out in one piece. To de-risk the works, it was jacked up in advance just to make sure it was free and confirm the weights precisely, because we were very, very close to the utilisation of the crane, and it was felt to de-risk it for everybody. The jacking operation was the best bet. It was picked up. We cored a couple of holes through the wings as they were, and then chain underneath, and out it came. Once it was out up on the road, although it was grouted, we still put in the control measures as if it's not. So steel plate and then crush over the ends just to prevent any fly. There you go, you can see it being lifted out. On the right hand side, you can see the new bridge going in. There was actually a pair of new bridges going in, but one either side. And interestingly, when you look at, excuse me, the tendons themselves, although it was shown to be fully grouted, there's not a great deal of evidence of grout within that duct there. When you look at those pictures, and even when you zoom in, there's a little bit of grout, but not a great deal. So it's probably a good thing that we put in place the, we put in place the precautions at either end. Not that the site team reported any fly or any loose debris being projected out. And there you can see one of the anchor plates at that end there. This is another fairly recent one. We were working for Sam Evans and Sons again, taking out this footbridge. Footbridge itself was of post-tension construction. We were responsible for the full demo sequence, the AAP, the crane position, the full whack on this one. That's the bridge itself. That's where the crane had to sit. We couldn't. There were constraints. I think it was network rail boundary somewhere that prevented us having putting more stick up on the crane, which then in turn determined or then made us use a different rigging arrangement, which meant we couldn't pick it up the sections in the current support conditions, which made things more complicated, but all things that can be dealt with. So the sequence was to lift out the drop spans and then work your way back down the structure. As you can see here, the columns were all verified to confirm they would stand up, and we did the full analysis of the structures and the pieces that were being lifted out. So we had the good historical drawings on this one, so we had a lot of detail available on the post-tensioning system, the tension they put into the system, etc. So we could determine quite well the likely effect of these lifting points on the works. So as I said, we could only put the crane boom out so far, which meant we could only use a size sliding modular spreader beam, which limited where we picked the sections up. So you're talking about a 17-meter long span, and we picked up 8-meter centers. So we had to analyze the sections and demonstrate that they would work with that change in that reversal of stress. You can see here the success, which proved it worked all the way through, and there they are on the ground to be broken up. Again, you're going from a simply supported span effectively to putting hogging into the system. So analysed it to demonstrate that it was safe and that the reinforcement within the structure could counteract the tensile forces, or could counteract the forces that we put into the structure when we changed the support conditions. That was all done and demonstrated to all concerned that it worked and would work quite happily. This span being the trickiest one, I think, to analyse was the cantilever span at the beginning. But again, it was all analysed and worked quite nicely. So things that went well, that were good, was we got involved early and coming up with concepts, which helped a lot. We can do the PT analysis on the structure, the 3D sequence that Cameron put together for us, and we're quite happy to stand our ground when Cat 3 checkers and the TAA want to have engineering discussions. A key point that I learned on this one is that not all checkers are that used to working with post-tension structures, and in fact the first Cat 3 check came back, said it didn't work. And the reason it didn't work is because they completely ignored the post-tensioning within the structure, which means it wouldn't work in the current condition, never mind when you're lifting it. So if you're using a company to Cat 3 check post-tension demolition, please make sure they have the competency to undertake checking for Cat 3 checking for post-tension structures. Not everybody can do it, or not everybody wants to put the effort into do it, should I say. But clients need to be aware that they need to really consider the competence of the people who are doing these checks for them. Okay. So if you want to know more about temporary works, demolition engineering, there's our webinars, there's the ICE book on temporary works, there's the iStruct temporary works toolkit, there's lots of things by the NFDC, temporary works forum, Safe by Design from Network